G'day nerds. So let's talk about enthalpy. And in this case, we're going to talk about what it is and how to calculate it from a practical standpoint. So this is your vocabulary. If I could just get you to pause the video here, write this down, and we'll be able to continue on, reflect on this as we continue on through our video. So what is an enthalpy change? First, delta H, which is our symbol for enthalpy change, is the comparison of potential energy, basically all the energy, the heat energy, which is stored in the bonds of the products. We're comparing that to the reactants. And because reactions go from reactants to products, we're actually seeing how much there is in the products minus the reactants. And that's all of the bonds in all of the products combined, all of the bonds in all of the reactants combined. So our change is, so delta H over here, the delta means change, formation. Now this means during the formation of elements, and H means enthalpy, at standard temperature and pressure. In other words, that's what the little zero symbol up here, or degree symbol, means. So what that means is we're going to use, to calculate the enthalpy change, the enthalpies of formation of all of our reactants and products. And we can just look these up in tables. So enthalpy of formation is a state product or state function, and this means it measures all of the steps from reactants to products regardless of the path taken. The only thing that matters when we're looking at our enthalpies of formation is what state it's in, basically, whether it's a solid, liquid, or gas, and they're all different. When we look at enthalpy changes, we need to be aware that an endothermic reaction will have a positive result, like a positive number, and an exothermic reaction will have a negative number. The SI unit that we use for enthalpy change, not enthalpy, but for enthalpy change, is joules per mole. And often it's joules per mole of reactant consumed. We'll have one reactant that we know the mass of, we can turn that into moles, and away we go. So it's joules per mole, but usually they're quite large numbers, so we end up going to kilojoules. But the SI unit is joules per mole, but kilojoules is where we tend to work. And here's our equation, right? So this is the standard equation. There's actually two derived equations we'll use, but they both come from this. So delta H for our reaction is the enthalpy of formation of the products, the sum of it, minus the enthalpy of formation of the reactants, divided by the moles of whichever reactant you want consumed, whichever one you can measure. So let's have a look at how we would calculate this in a theoretical sense. And we're going to use the combustion of methane. Methane plus 2 oxygen gives us a carbon dioxide and 2 water molecules. So in this case, we'd use this derived equation. So our delta H of our reaction is equal to, so enthalpy change of our reaction, so RxN, short for reaction, is equal to the sum of the delta H of the formation, so enthalpy of formation of the products, minus the sum of the enthalpy of formation of the reactants. So that's the enthalpy of formation of our reactants. And we multiply these by our coefficients in the reaction. So when we find the enthalpy of formation of water, we'll multiply that by 2. Oxygen will multiply by 2, but the enthalpy formation of an element in its standard state is 0. So that'd be 2 times 0. And again, we're talking about the sum of enthalpies of the formation of all of our reactants multiplied by their coefficients. So again, these are standard state functions. And we look these up in tables. So we're looking at theoretical calculations. We can actually look this up in a table. Delta H for our elements in their standard state is 0. So here we have all the species in this reaction. We've got methane, oxygen, carbon dioxide, and water. And here we have the delta H of formations for them. It's a negative 74.81. So to go from carbon plus hydrogen to get this into methane is an exothermic reaction. Here we have an exothermic reaction and another exothermic reaction. And that is to build these out of our standard states. Now, Remember, this one here is a 0. So let's look at how this works. It's actually not too simple, not too confusing, sorry, once we're in there and practicing. But also, actually, note that the water, because this is a combustion reaction, is a gas. And that's a different value to if it was a liquid. It's a bit higher, I think. So, delta H equals the sum of the formations of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants, and we add these in, right? So here we've got so here's our carbon dioxide plus 2 times our water, so that's our products, minus methane plus oxygen. It's actually 2 times oxygen, but oxygen is a 0. So here's that next step, animated weird. So this becomes carbon dioxide minus the water. Again, we've just multiplied it there, that's all. And it was a negative, so it becomes a negative. This one here is a negative being subtracted, so that becomes a plus, which means we end up with negative 877.1 plus 74.81. And these are already in kilojoules per mole. Remember, these numbers tend to be quite large. So this gives us a negative 802.29 kilojoules per mole. This means it's an exothermic reaction that will release negative 802.29 kilojoules for every mole that we burn. Or, because we're scientists, actually this is wrong. That's an error. That should be negative 8.02. Get rid of that 3 there. Times 10 to the 2 kilojoules per mole, because, say, oh no, that's correct, sorry. Because we have 4 significant figures, just cheat there and make that couple of extra significant zeros on there. But it's an absolute 0, so that we don't have to count that one. All right, so let's look at our practical calculations. Obviously, we've got a little thing here with the animations, whatever's. So our delta H of reaction is inversely proportional to the heat released, which is Q. There's another video for that one. Basically, what this means is we can actually measure the heat of reaction, or sorry, the enthalpy of reaction indirectly by measuring the heat of reaction, or the heat it releases. So we can measure the heat, and we can use that to work out the enthalpy. So back to our standard equation, if it's, sum of the products minus sum of the enthalpy formations of the reactants over the moles, that becomes, again, because they're inversely proportional, negative Q over the moles, or negative MCAT. Remember the delta T, so it's not really an MCAT. It's minus MC delta T, and that will be in Kelvin, divided by the moles. And we see that here. Right? So here's our reaction written large. M is the mass of the substance being heated, usually the water and the calorimeter if it's from underneath. C is the specific heat capacity of the substance being heated. Again, usually water, but if we're doing it in a can calorimeter, you'll actually do the MCAT twice and add them together, but you'll divide it by the moles only once, and delta T is the change in temperature. N is the moles of the reactant consumed. Now let's have a look at this equation. So, if we have 0.831 grams of glucose and we burn that, and we heat up 100 centimeters cubed or 100 milliliters of water, which is 100 grams of water, by 17.3 Kelvin, let's calculate the enthalpy change of this reaction. And we need to remember the specific heat capacity of water is 4.18 joules per grams per Kelvin. So let's have a look. First step, write the equation. Boom, smashed it. Glucose. And that's glucose being combusted. Now, we're burning it, so it's a gas, which is a bit different to respiration. We want to calculate the moles of the reactant. Okay, we've got the 0.831, and that becomes 0.831 over the molar mass of glucose, which is 180.156 grams per mole, which gets us to 4.61 times 10 to the negative 3 moles. However, we're actually going to use this section of this in our equation, and we'll show you that in a sec. Now we want to calculate the delta reaction of enthalpy, or skipped ahead, delta CH, and the C there means combustion. So let's have a look. So delta CH is negative Q over N, or negative MCAT, over 0.831 divided by 180.56. Now, this helps us keep our math straight and check our working if we include this in here at all times instead of just storing it in our calculator. You can store it in your calculator, but this is a better way to do it. So what this becomes is it becomes negative, because of the negative there, 100 times 4.18 times 17.3, okay, divided by 0.831 divided by, so in brackets or parentheses, 180.56. And that gives us this number here, minus 1,571,241.3 joules per mole. And now you see why we tend to run in kilojoules. So that's negative, so our enthalpy of combustion is negative 1,571.24 kilojoules per mole. Now there's a little thing we have to do first. So we have our answer statement, really important. Therefore, the enthalpy of combustion of glucose is negative 1.57 times 10 to the 3 kilojoules per mole. Now, we write it in scientific notation into 3 significant figures, because if we look up here, 3 significant figures and all through here is the best we have. Or, alternatively, this is another way to write that answer statement, 1.57 times 10 to the 3 kilojoules per mole is released when glucose combusts. And you'll see when we talk about the enthalpy change, it's a negative, but if we talk about the heat which is released, it switches it to a positive. So that's actually the relationship between heat and enthalpy. It's been a long one. Thanks for sticking in there. I hope that made a lot of sense. And if it didn't, put any questions you have in the comments below, and we'll get to you as quick as we can. Thanks for watching. See you next time. Bye now.